Hello, everybody. Welcome to the May installment of our monthly club astronomical meeting. We have a pretty awesome meeting tonight and an interesting speaker and some interesting activities going on. So I'm excited to get started. Just to let everybody know, we're recording this and we're going to post it to YouTube later. So without further ado, our agenda tonight, we'll have a couple introductions, some announcements of club activity stuff, and then our featured speaker, which we're very excited about, is coming to us from around the world with very little lag, and coming to us from Friday morning. And then we'll just talk about what's going on for observing a couple of things, solar and shallow sky stuff this installment, do our images, and then wrap things up. So in terms of introductions, I would like to open up if there is anybody who is a guest, or not a member or first time here and wants to just say hello and introduce themselves. Anybody new? Anybody new who's not shy?
I'm shy, but I'm Glen, KC3TBL. I got the invitation from the Columbia Amateur Radio Society.
Great, welcome. I was expecting more of your colleagues here, but I guess you can pass along the meeting, the good word, and the fact that they can watch it later on YouTube.
Excellent.
So welcome. You used to be an astronomer too?
Yes, I'm retired now, but I worked at the Space Telescope Science Institute in Baltimore for 37 years.
Wow. So we have some people in common, because we have some people in the club that are and have also retired from the Space Science Telescope Institute.
I probably know them then.
Okay, well, maybe we can talk offline after the meeting ends.
Sure.
If you're able to stay on the whole time, we can chit chat near the end, the wrap up and discussion section. So great, welcome to the meeting. Anybody else want to say hello? All right, well, we'll go ahead and get started. If anybody's new or comes on or wants to say something at some point, please jump in. So announcements, star parties. We have a star party coming up. Members only star party this weekend on the 20th at Alpha Ridge Park, and the following week we'll have a public star party. Hopefully we'll have some good weather for our first good weather star party event, and we can have lots of members of the public, etc. Also, in terms of regional star parties, one of the ones that is often, of interest to our club in Pennsylvania is coming up in June. And just a reminder, if you're interested in that, you might want to sign up, because it can fill up. So if you want to get to those really nice dark skies up there in Cherry Springs. Next topic is Astro School. Bill, you want to take it?
Yes, so excuse me, as a reminder to everyone, Astro School is officially been launched. We had our second in a row monthly session. The first one was done in the planetarium over at Robinson Nature Center, led by our own Bob Savoy. And if you thought you enjoyed that one, if you were there, his presentation he did on Saturn and Saturn's rings last Thursday in person was really excellent. I mean, Bob really put the time into it, and we're not a uninformed audience. We all know a little bit about a lot of things, or some people know a lot of things about a lot of things. But Bob really, really presented Saturn and Saturn's rings in ways that for me it was things that I had never known before that were fascinating. And if there was anybody else, I know Daniel, you were there, and you can see who was in the room: Arjun, his dad, Ken, Crystal. If you guys want to add anything to talk about it, please go ahead right now and mute yourself real quick and jump right in. And then we'll talk about future stuff for a minute. So Daniel, did you enjoy the session on Saturn?
I did. I really learned a lot.
So that's great. Anybody else? So Bob, it's really much appreciated now. So what our plan is the second Thursday of every month at the Robinson Nature Center at 6:30 to 8:30. We're planning on doing a topic. And if there's a topic that you would like, you're interested in, this is about you guys providing us the information. We may not be the subject matter experts, but we'll get somebody who is to do the presentation, and we'll just continue to be the host. And it could be on anything. People have talked about how to properly clean eyepieces, how to set up new telescopes. I mean, there's all kinds of things that we're going to do. And over the summer, with the date to be announced, be a Saturday or a Sunday morning, or later morning, we'll do a solar session out at our observatory out at Alpha Ridge Park. Because obviously doing that inside the building over at Robinson Nature Center won't work. But so that'll be part of an Astro School. It's just a very focused on one topic, and it's well received. So if there's any questions, I'll take them. If not, turn it back to you, Victor.
Okay. Well, that's great. I love it. And if anybody wants, again, we'll have open discussion at the end if you want to wait until the end of the meeting to talk about topics or whatnot. Next slide. So Crystal has indicated that she was going to be a little bit late today. So rather than me talk about this, I'm just gonna defer to I have her notes and her notes about this, but I'm gonna just wait, and then when she comes on later, we'll revisit this. But this is the book of the month. If anybody wants to record it, I know I'm going to download it and start. I'm looking forward to it. Okay, so without further ado, I would like to invite our speaker.
All right.
I would like to just say a word or two, if I can get myself organized. Sorry. So Glen is the Commonwealth Scientific and Industrial Research Organization Communications Officer for the Canberra Deep Space Communications Complex. He has been there since 2002 and focuses on educating and promoting space science to the wider community. That's a function that's near and dear to our club's heart. So especially the younger generation, with the goal of exciting them about engineering, science, and mathematics. He's been in the career for over 38 years and has worked with organizations to promote international and domestic development of space science and related services and technology, and has supported several space conferences and industry groups. He's been an active grassroots promoter of science to schools and public, and shares his enthusiasm through public speaking, i.e. tonight, and media appearances. Glen has also worked at the Cicero's Parkes Radio Telescope, the Australia Telescope Compact Array, and is currently also supporting NASA operation activities at the Canberra complex. So without further ado, I would like to invite you to speak. Thank you for being here, Glen.
Thank you very much for the introduction, and thank you both to Victor and to Phil for inviting me, and an apology for not being able to be with you last month, but surgery required me to be there, and so feeling a little bit better today, although battling a sore throat. all that being, what I thought I'd do by way of introduction, and you probably got a sneak peek of it a little bit earlier, is just actually start off with a little short film, which I think is a great way to just to introduce you to the work that we do at the Deep Space Tracking Station, and most especially the people that do this job of communicating with our spacecraft across the solar system and beyond. So I'm going to do my share screen and go over to here. So sharing that. And play. Give me a thumbs up if you've got sound as well.
No sound.
No sound. Ooh. I could play the music. Hang on.
I don't hear anything.
Yeah, you may need to enable desktop audio, but it's a difficult setting to find if you hit the speaker button with the arrow.
Is that a Zoom thing? Is that me? Do I need to do that?
It's not you, Victor.
It's the share.
Right, it's in the share. So,
Yeah, it's not. If you don't know, it's like kind of confusing, but
yeah, Victor, open your share thing and look under there or under security tab and see if there's a setting you need to do for audio. But it really shouldn't be necessary. It should just,
It's not on, I don't have anything on my,
well, it's good to know that in Australia they have technical issues with the computers like we do on this side.
What kind of computer are you using?
Glen's muted at the moment.
Yeah, and Glenn took his headphones off, so he probably doesn't hear us.
Pretty cool looking video. I'll ask Glenn this if he comes back online, but he mentioned the Parkes telescope. I think there's a pretty interesting movie about that telescope called The Dish. I think it's about that telescope and about how that was, how it came into play with one of the Apollo missions. If you haven't
It
seen
was
it, it's
Apollo
pretty-
11.
Okay, thanks. It's a pretty good movie if you haven't seen it. It's fun. It's a nice movie. We came online to do a test early on, but we forgot to test the sound.
yeah, the video's I think only another minute longer, and the closed caption is helping. Very cool.
Oh, hey, we've seen a couple of those things.
Yeah.
It was dark there for a second.
or it's quite often much easier to actually communicate with spacecraft at Mars than it is to. Hopefully you caught me there. So I'm just trying to get out of this. Back to me. All right. So hopefully you caught some of the audio on that. It's actually easier to communicate with spacecraft at Mars than it is to actually do things via Zoom sometimes. All right. You still have me as audio?
We do.
Great. All right. Thank you. All right. So nothing else that I have tonight that tonight for you that I'm going to talk about has sound. So I'm going to go to another set of slides here. And this is going to be a little bit easier, hopefully. And okay, and you should have that slide, hopefully.
We do.
Great. All right. So yes, so I work for the Canberra Deep Space Communication Complex, part of NASA's Deep Space Network, one of only 3 places in the world that has this important task. And that's to provide all the communications to the many dozens of robotic spacecraft that are out there exploring our solar system. Spacecraft visiting planets, moons, asteroids, and comets, looking deep into our universe, other stars and galaxies, watching our own star, of course, our sun, all day, every day, and then a range of other spacecraft that do keep a broad eye around our corner of the universe here on planet Earth. So our job every day, we're basically kind of mission control. We send commands to spacecraft telling them where to go, what to do, what not to crash into, unless we want to crash into it, and what information to collect for us and send back home. We're doing all of that work, of course, via radio communications, using radio waves, radio signals. But in the future, we'll be moving into higher and higher frequencies and eventually take the leap into optical communication over this next, well, literally 5 to 10 years. That will be the big change for deep space communications. In this slide there, you can actually see a nice aerial view of our complex. We're situated in the Tidbinbilla Valley, which is located about 35 kilometres outside of Canberra, our nation's capital. It's a beautiful valley location, and we're, of course, site dominated by our giant antenna dishes, which I'll get into a bit more detail as we go. We have about 85 people that work for our complex. They're great engineers, technicians, spacecraft communications people. So we don't have scientists here. That's usually the thought that most people have, that we're all scientists here. We do have one who's our resident radio astronomer who gets to use spare time on the antennas. But for the most part, our people are people behind the scenes who make sure that the antennas are constantly operating, that we are in constant contact with the spacecraft in our tracking schedules. And as I mentioned, we're handling quite a number of spacecrafts at the moment, 50 missions spread out across the solar system at the moment, representing 27 nations around the world that are exploring our solar system and beyond. And I worked it out the other day. It comes out to about $33 billion of spacecraft that we're responsible for. And of course, more missions are going all the time. So in terms of a dollar value, not really important from the science point of view, but when you're talking to some of the people who handle the money behind the scenes, particularly at NASA headquarters, and they're talking then to the people that hold the purse strings within government. It's always important to say, it's all about the money, not so much, about all the great science those spacecraft are doing, because it's a little bit easier for them to understand and appreciate. Our operating budget for the station, though, is actually relatively small. It's about $16 million US per year, which translates to about $24 million Australian. Most of that money is just paying people's wages. And the next biggest bill is our electricity bill, because it takes power to do all the work that we are doing. We're also busy with our education work, seeing about 12,000 students per year. Myself and my colleague, Corinne McDonald, that will look after our visitor centre and public services. The Deep Space Network, of course, 3 stations around the world. So we have our station here in Canberra, of course. There's one in a place called Robledo de Chavela, which is about 60 kilometres southwest of Madrid, Spain, and your own station there in the United States in Goldstone, California, in the Mojave Desert, about 200 miles outside of Los Angeles. And between the 3 of us, we provide 24-hour coverage of all the different robotic spacecraft out across our solar system. Here in Australia, as Victor mentioned earlier, I work for the CSIRO, which is our national science agency. They have a number of different divisions working in areas of agriculture, mining, radio astronomy. They do marine research, agriculture, a whole range of different things. But we have part of a particular business unit within CSIRO, and that's the Space and Astronomy Unit, part of the Digital and National Facilities and Collections program within the CSIRO. And we have a number of facilities that CSIRO is responsible for around the country. They are our contractor on site here at our station here at Tidbinbilla in Canberra. The way that the station operates, of course, we're part of NASA's Deep Space Network. The Jet Propulsion Labs look after all the interplanetary missions, and a section of JPL called the Interplanetary Mission Directorate. And that's this job I would like to actually have working for them, because there's somebody there called the Director of the Interplanetary Mission Directorate. And that's, I think, probably one of the best job titles of all time. So they look after interplanetary missions and the Deep Space Network at JPL. And then in Australia, we have then our local science agency manage the station on JPL and NASA's behalf. That way NASA does not have to have personnel here. They do a similar thing at the station over in Madrid, Spain, where the Spanish space agency INTA and a local contractor called ISTEFE look after the day-to-day operations of that actual site. So it's a nice host nation agreement. It stood as a treaty arrangement between Australia and the United States and Spain for more than 60 years now, and will be certainly ongoing into the future. The CSIRO also look after a number of facilities, a couple of places that I've worked at, the Parkes Radio Telescope up in central New South Wales. It is famously known as the Dish, probably one of the prettiest radio telescopes on the planet, and is certainly still the world leader in particularly pulsar research. That has more pulsars credited to it for discovery than any other antennas, all the other antennas in the world combined. There's also the smaller MOPRA antenna up in northern New South Wales, and the compact array at a place called Narrabri. It's actually, and you can see 5 illustrated there in the top right-hand corner. There are actually 6 antennas on a long railway track, and those antennas can be moved in any positions along those tracks, doing very long spaceline interferometry, the ability to connect multiple antennas together to act as a single ear on the universe. And we collaborate quite closely. When we're not doing spacecraft tracking here in Canberra, we will do a little bit of radio astronomy work in our spare time. It's usually only maybe 1 to 2% of our year. And we can combine our antennas, again, through that VLBI process, connect our dishes at Tidbinbilla, the Parkes Radio Telescope, the MOPRA antenna, and the Narrabri antenna to create a dish that's over 1,000 miles in diameter. So that gives us a very powerful instrument to do observations of the far distant universe at great resolution. In Australia, also over on the west coast of the country, over in Western Australia, you can see on the left-hand side of the image there's a couple of facilities, and the particular one there at the top left is the Murchison Radio Observatory, MRO, at a place called Bullardy in the isolated regions of Western Australia. It has a population density of 1 person per 10 square miles. So it's not very many people out in that region, but it makes it an ideal spot for radio astronomy. And what the MRO is a part of is the Square Kilometre Array project, connecting multiple radio telescopes in Western Australia and South Africa to create a permanent VLBI antenna about 1/3 the size of the Earth. And ultimately, they'll be also building over 132,000 smaller mid-range, mid-wave radio telescopes that look like small Christmas trees, metal Christmas trees sitting on the ground. And there'll be a huge swath of those right across the Western Australian region, and almost creating a radio telescope on its own about the size of, I'm trying to think of an equivalent US size. So imagine a radio telescope going from Los Angeles over to almost Mississippi. That's a pretty big radio telescope on its own, and will be able to be a very powerful instrument to be able to collect data from the far reaches of the universe. Even just at the small scale of that radio telescope now, it's collecting more data every day than currently exists on the entire internet, and that volume is only going to increase. To process all that data, the CSIRO has set up the Pawsey High Processing Centre in not far from Perth, over in Western Australia, and translating huge volumes of data through there each and every day. There's other radio telescopes, sorry, I should say spacecraft communication telescopes in Australia, particularly at Nunorcia, and that's the European Space Agency's 35-metre antenna that they have located there, one of 3 sites that they have around the planet to support European missions. Although here in Canberra, we're also supporting their missions quite often for the Western Australian site, and there are other 2 sites around the planet. They're really only handling missions out to Mars distance. You would probably know recently they launched the JUICE mission off to Jupiter, the Jupiter Icy Moon Explorer, and they'll be doing some communication for that. But the Deep Space Network will swing into work for that once they actually get to Jupiter space. So yes, quite a range of facilities across the country that we're involved in. The way we work, and this is sort of the dry political stuff. I mentioned already we have a government-to-government arrangement between Australia and the United States, a treaty-level arrangement, and then we have the agency arrangement. So NASA is your space agency. Australia does have a space agency now, but the direct link for the deep space communications is back to the CSIRO, our National Science Agency. There are interlinks between the CSIRO and the Jet Propulsion Labs, as are the links between NASA and the Jet Propulsion Labs. All the information and the work for deep space missions through the Interplanetary Mission Directorate, and then all of that work coming back to us here in Canberra. The same arrangements operate for the Californian station and also for the Spanish stations as well. Just as an important note, and I mentioned earlier about the finance, all of the operation costs of the Deep Space Network comes from NASA's budget. So it is a shared operation. We pay all the bills locally. NASA pays for all the communications work that needs to be done. And other countries, all the different nations that we're supporting and using the Deep Space Network, support that network on a user paid basis. Effectively, to communicate with a spacecraft, they have to build this into their budget that for each hour, there's about $1,056 for the first hour of communications, and it comes down to about $400 an hour after that, which I'm sure is still much cheaper than, say, any of your telcos could do in the United States for deep space communication. We're not only doing our spacecraft communication, there's a lot of work that we do in radiometric tracking and spatial commanding and control. We do a lot of software and systems development here at our site in Canberra. We're kind of the station of excellence for software development, and a lot of the software that we create here gets distributed right across the Deep Space Network, and other systems that NASA also use for near-Earth communication. So each of the sites, because of their long history, have all gained particular areas of expertise, and we all share that equally around, and it's just done just so that we can do the job far better. The Californian station's got very good at automation work, so a lot of automation of the communication work we do has come from there, and some of the engineering aspects to improve the way we do things. The Spanish station has gotten very good in that area. We all have our expertise in all those different areas, but then we make sure that those specific areas that we can focus on and be able to share that information out there. Apart from all the radio science and spacecraft communications, we also do some near-Earth asteroid observations. So you've probably seen through the Californian station, they have the Goldstone Solar System radar, pinging signals off nearby near-Earth asteroids, getting these sort of ghostly radar type images. And those images then, or the signal is then received at another ground station. Usually for the United States, it's the green bank antenna in West Virginia. For us here in Canberra, we relay our signals off the asteroid into the compact array up at Narrabri. The Spanish are also using some other radio telescopes that they have across Europe that they can access to do that kind of work. So there's a lot of collaborative work that goes on between the deep space communications systems and the capabilities we have with our high power transmitters to the radio telescope receivers that are dotted out there, so that we can keep an eye on these nearby Earth crossing asteroids. For the site, as I mentioned earlier, you saw that the very first slide, that overview, the aerial view of the site. It's dominated by our big dishes, and this is Deep Space Station 43. It's the largest parabolic steerable antenna in the Southern Hemisphere. It's still one of the largest antennas in the world used for spacecraft communications. Whenever we're talking about sizes of antennas, we're always referring to the diameter of the dish. So our big dish here is 70 meters, 230 feet in diameter. Across the curvature of the dish, that's actually 109 meters. And so you could place an entire football field inside that dish and still have plenty of room to sit around and watch the game. The entire antenna stands about the height of a 22-story building, and just the dish and its moving structure weighs some 4,000 tons, 4 million kilograms. So that's about 8 million pounds of weight in that particular antenna. And that's just the moving structure. The base weighs about another 4,500 tons and is locked into granite bedrock about 30 feet underground. So it's a very big, very stable structure, doing amazing work every day. Imagine taking a 22-story building and turning it on its side and spinning it around every day. It's effectively what this dish does. Two simple drive mechanisms. It has the big curved gear underneath the dish, 4 big bull gear driven motors. Each of those motors about the size of a car, with a 1 to 244,000 gearing ratio. So that gives us incredibly accurate motion in elevation. And the dish can go from a fully upright position to right over on its sides. The leading edge of the dish is only about 4 feet above the ground, and do that move in about 3 minutes. So it's quite amazing to see such a, a football stadium sized antenna being moved at that kind of speed. A rotation on the base uses a hydrostatic bearing. So think of it being a little bit like a hovercraft. It's using the oil pressure rather than air pressure, floating that antenna on a film of oil that's only about the thickness of a sheet of paper, but creating a virtually frictionless bearing so that we can easily rotate the antenna on the base. So between rotation, azimuth, and elevation, we can turn the antenna to any point in the sky with better than hair width accuracy. It's 0.005 of a degree pointing accuracy. Apart from the big 70-meter dish, we have 3 operational 34-meter antennas on site. And just to define the numbers here, all of the antennas have a 2-digit designation. So our big dish, Deep Space Station 43, and then we have antennas, Deep Space Station 34, 35, and 36. In Australia, we have all of the antennas in the 30s and 40s series. At our Spanish stations, the antennas in the 50s and 60s. And at the Goldstone in California, it's the antennas in the 10s and 20s. So for our big dish, Deep Space Station 43, in Spain, Deep Space Station 63, and in California, it's Deep Space Station 14, because 13 is an unlucky number. We're as superstitious as anybody else, and Deep Space Station 23 was already taken, so it gets the designation of 14. So the 3 34-meter antennas, so about, just trying to work that in it's about 110 feet in diameter. I'm doing my translation of metric to imperial in my head. It's good fun. Good mental exercise for, I think, our youngest person on the call there. He needs to be thinking in metric for our future if he's going to be a great engineer. So the 3 34-meter antennas are what we refer to as beam waveguide antennas. So unlike the 70-meter dish, and you can see in the center of that antenna, that central cone structure, that's the antenna's transmitter and receiver system. Just to give you a nice sense of scale, that cone structure is the height of a 5-story building. So, you've got a 5-story high building sitting inside a sports stadium-sized dish. It's quite an amazing thing. For the new antennas, they actually don't have those cone structures in the dish. The new generation of antennas have all those systems underground. So you can see in these photos, there's a little roadway, and I hope you can see my mouse moving on the screen, perhaps there. They have little roadways that run underneath them. And underneath here is a 2.5-story deep cylinder. And that's where the electronics, the transmitters, receivers, and the power systems are housed. So for these antennas, radio signals coming in from space bounce off the parabolic dish surface, that reflects it to the subreflector, the secondary dish at the top of the antenna quad structure. And then that focuses the signal down through a hole in the center of the antenna. It takes it through a long tube, which is a little bit, it's like a periscope, but using metal mirrors, dichroic plates, to be able to bounce that radio signal down around the elevation drive system and then down into the receiver system underground. And if we're then transmitting, it's up through that tube and then out through the middle of the antenna, the subreflector, off the dish and out into space. So for the housing all of that electronics underground does a number of things for us. Unlike an optical observatory, which sits high on a mountain, away from the obscuring lights of towns and cities and as high above the obscuring effects of the atmosphere as possible, light pollution is the enemy there for optical observatories. Our enemy is radio pollution, radio noise, radio frequency interference. So one of the reasons we're in a valley, first off, is to shield us from that line of sight radio noise coming from the local region, from radios, televisions, and cell phones, and so on. And then by having all the new antennas, the 34-meter antennas, having the electronics underground, that does a further step of isolating that electronics from that radio frequency interference. So it also creates the ability for taking quite delicate and expensive equipment, not having to lift it on cranes to put it into the dish. You can just bring it in by a vehicle underground, so you stay at ground level. It also means we can keep the electronics more temperature stable, being underground in that sealed environment, and it's safer for people. They're not having to work at heights as often. They can work simply at ground level in a more comfortable environment, because temperature ranges in Canberra from about, well, as it was this morning, around about -4 degrees Celsius. So pretty cold, but we get 40-degree Celsius days here in summer. So you're looking at temperatures from, translating at the top of my head, probably from about 10 degrees Fahrenheit to maybe well over 104, 105 degrees Fahrenheit. So keeping it underground keeps it all temperature stable and keeps the electronics much happier and keeps the engineers happier too. So for these antennas, they work in a wide range of frequencies, and along with the 70-meter antenna, we can handle everything here from about 2470 megahertz up to 32.3 gigahertz. So we're getting up into the high Ka bands. But as I mentioned, we will be actually moving into optical frequencies in the years to come. Right at the moment at the Californian station, they are building a new 34-meter antenna, which will be known as Deep Space Station 23. The former 23 was retired, so this new antenna gets the old designation. And it is going to be the first of the hybrid antennas that the network will build into the future. Hybrid by way of they'll be doing both radio frequency and optical communication. In the central area of these antennas, they're going to cover the surfaces in these large hexagonal mirrors. And those mirrors will be capable of receiving in the sensors with them in the near infrared ranges, and be able to receive optical communication from deep space missions. The first mission that will take advantage of that will be the Psyche mission, launching later this year, going off to the asteroid Psyche, possible remnant core of a protoplanet that was developing in our solar system billions of years ago, but ran out of material to continue growing to become an entire world. And that spacecraft will have not only its radio communications, which is standard for all spacecraft, but will have the first deep space optical communication capability. This will be only for receive only at the moment. Uplink is still being worked on at some more complications, just simply because of the exponential spread of the signals from spacecraft. While we can have large receivers here on Earth, it's very hard for a small spacecraft out in deep space to have as large a receiver. It's fine for radio, but optical still presents some challenges there. For all the antennas on site, they are all operated here directly on complex. And we also have with the other stations a system that we call follow the sun. So follow the sun operations means that during daylight hours at each site, that station runs the entire deep space network. So I'm talking to you from Friday morning at 9:48 local time. And so from our control room at the moment, you can see a nice panoramic view of our control room there, which is a little bit like an air traffic control center, multiple consoles operating there. From those consoles, those teams can operate not only the antennas here in Canberra, but the antennas over in Spain and California. And that's what we'll be doing right now for about the next 8 hours or so. We will then hand over, as the Earth continues to rotate, we'll hand over to our colleagues over in Madrid, Spain. They'll take over the operation for the entire deep space network. They will then, after their day finishes, hand off to the California station, who will then operate the network there. In years past, it used to be before we could do this kind of communication work, relaying between each of the stations before we had those direct connections. It used to be just that station running its own antennas 24/7, and there were people in the control room at all times doing that kind of work. And now you can just have a daytime crew, so it presents a much better lifestyle for the operators in there, many of them who have been working in that control room for, well, I think the youngest person operating in there has been there for 21 years. Some of the people in there have worked in there 35, 40 years in one case. So they're probably due for retirement fairly soon, I would think.
Hey, Glenn,
And so, yes, go ahead.
can I ask you a question?
Yeah.
Hey, so when you were talking about the all the electronics and stuff being underground,
Yes.
I hear right that that first receiver, after the signal bounces off the secondary mirror for
The sub-reflector, yes.
receiver is underground also? The first receiver for the signal is underground, or is that
Yes, yeah, yes. So it's the dishes are a Cassegrain design. So with that secondary dish, let me take it back to the 70-meter shot. So yeah, signals off the dish surface to the secondary receiver. That secondary dish is asymmetrical in shape as well.
Right.
So it can be moved in multiple axes to account for deformation in the dish surface through temperature, expansion, contraction, or even gravitational sag. As the antenna moves over on its side, you'll get the top edge leaning in a little bit more than the lower edge. But yes, and those radio signals then come in down through the various receivers. So there are a number of receiver horns on the central cone structure there. Yeah.
This is where my question comes in. So, you know, the picture here with those horns there look different than the other radio telescopes where it looked like there was a hole there.
Yes.
You know, with the sensitivity of everything where those holes are, I was wondering if weather, like rain, it travels down that like a drain in a sink and causes a disruption because it's, you know, in the other radio telescopes that I've been around, the receiver is actually attached to the large receiving dome after it bounces off, you know, right in the horn. It's all right above the weather and everything's able to be shielded. But this looks like it's a giant drain that's going to take not only the signal, but all the weather and debris and everything else that might blow around. Is that something that happens, or is that just my imagination going crazy?
So yeah, quite often as people ask us, don't the dishes turn into giant bird baths, you know, filling with water? But across the surface, and I wish I had a convenient shot to show you, but across the surface of the receiver horns, there is a mylar covering.
Okay.
So it's a transparent mirror for radio waves, but then keeps water and insects and anything out of the receiver horns. For the 34-meter antennas through that surface, there is a mylar covering across that entire surface. There's also a very thin wire mesh, and that's to stop, strangely enough, pigeons from getting in and deciding that that's a nice little hiding place to build a nest or something like that. So yes, the drainage issues, not a problem of water coming down in through there. It does look like an open hole, but there is actually a mylar covering on that to stop water from entering the receiver system.
Great, thank you. Yeah.
And so, yeah, for our control room, a great team of people. There's usually about 8 to 9 people at a maximum in the room. So they're handling anything up to 3 antennas each. They can be in any locations, anywhere on the planet in the Deep Space Network, and handling potentially up to 7 spacecraft at a time. Most especially when we're doing communications with Mars. And there are so many missions at Mars at the moment, it's considered the traffic jam of the solar system, that really the operator just has to point the antenna at the center of Mars, and the signal footprint overall is large enough to capture all of the spacecraft in orbit around that planet and on the Earth-facing side of the surface of that particular planet. So we developed a system here in Canberra, which the entire network uses. We call it MSPA, multiple spacecraft per antenna or per aperture. And that allows you to actually bring down data from 4 spacecraft simultaneously while uplinking to a 5th. So this helps to increase the capacity that we have for the antennas. Rather than just having one antenna, one spacecraft, you would need an individual antenna for every single spacecraft that's out there. And we can't afford to build 50 antennas and more. So developing that MSPA system allows us to capture data from many spacecraft at the same time, as long as they're in a similar location like Mars. So once we have, over the next couple of years, multiple missions heading off to Venus, we will also use that MSPA system to be able to keep up with all the data demands that are required by those particular missions. So the control room, basically the heart and soul of the station, but is supported by the 80 other people that work around the entire site, making sure all those systems operate perfectly 24/7. Right now, as I said, we have about 50 missions across the solar system. Our most long-lived missions are the twin Voyager spacecraft. Voyager 1 and Voyager 2 launched in 1977. I always like reminding kids that the Voyagers left Earth just a couple of months after the very first Star Wars movie came out, the good Star Wars movies. Those 2 spacecraft did an amazing job going and doing their flybys of Jupiter, Saturn, Uranus, and Neptune, finishing that task for us in 1989. Since then, they've continued to travel out into deep space at about 17 kilometers per second, covering about 1.4 million kilometers per day. They have now left behind the termination shock and the Helios sheath boundary around our solar system. Both Voyagers are now in interstellar space, the space between the stars, with Voyager 1 now being our most distant at 23.8 billion kilometers from home. So it's, was that more than 18 billion miles away. And we still talk to both Voyagers every day. They're still telling us new and unique things about a region of space far beyond the planets, now outside of the magnetic bubble of our sun that surrounds our solar system, and helping us learn more about the interstellar medium and the high energy particles, high energy particles streaming through our galaxy that are bounced around our solar system by our Helios sheath. And yes, keep going.
I have a question.
Yeah, go ahead. Anytime.
Michael, you want to go ahead?
Yeah.
Thanks, Victor. Yeah, I had a question as far as Voyager 1 and its speed and distance in relation to New Horizons. So Voyager, launched in 77, New Horizons launched around 2010, but New Horizons was the fastest object to leave, or at least exit, our solar system. Any idea at which point New Horizons will catch up to Voyager?
So it will never catch up. And actually, New Horizons was the fastest launch from the Earth. They used a very powerful rocket for, what is a relatively small spacecraft, and to get, maximum acceleration for that vehicle, because it needed to catch up with Jupiter only just over 14 months later. And that's really moving. So its speed is around about just over 14 kilometers per second. So it got the gravitational assist from Jupiter to send it on out there. For Voyager 1, particularly Voyager 1, it got its acceleration from Jupiter and Saturn. So it got a really good 2 big gravitational kicks to get it up to the speed that it's traveling at now, just under 17 kilometers per second. So the New Horizons spacecraft will never catch up with Voyager or overtake it. So there's the difference between that Voyager at 17 kilometers per second and New Horizons at 14 kilometers per second.
Okay, thank you. And that's fascinating.
No problem. For Voyager 2, it's traveling a little bit slower. So while it got gravitational assist from Jupiter, Saturn, Uranus, and Neptune, it's traveling at just over 15.5 kilometers per second. So it's still moving at quite a great speed. But again, New Horizons won't catch up with it. The Voyagers also overtook the Pioneer spacecraft that were launched in the 60s and 70s that are also heading out of the solar system. So they are our most distant explorers, and will be for quite a while. I would think that it'll take a while to get spacecraft going fast enough to be able to catch up with those craft. And at the moment, there's nobody, sponsoring a mission or funding a mission to be able to send the spacecraft just to leave the solar system. This is total bonus, mission time with the Voyager spacecraft. Remembering that they're only designed for originally designed for a 7-year mission, get in Jupiter and Saturn. If all was well, then you would have Voyager 2 go off to Uranus and Neptune during that unique lineup of the planets that only happens once every 156 years. And then to send them out and have them still working after more than 45 years to get to interstellar space. And the spacecraft designed, with recording systems on board, which are literally 8-track tape, for all those of us who remember 8-track tape, and total memory on board available beyond the operating system. There's only about 128 kilobytes of memory available for data recording on the spacecraft. So they've done incredibly well to still be out there after more than 45 years. We think we'll still have contact with them for at least another 10 to 15 years, although they will turn off the last science instrument sometime now. There's been a stay of execution on that until probably 2028 now for Voyager 2 particularly. So we'll still get a few more years of science out of them, but then eventually the last science instruments turned off on both, and it will just be the carrier signal only. They will continue their journey off into deep space, and at Voyager 2's current flight speed, covering about 1.4 million kilometers a day, it'll reach the next closest star on its flight path in just another 296,000 years. So it's still got a long way to go.
Are you okay?
Yes, keep going.
Are you okay fielding questions while you?
Please, yeah, please do. It saves me having to continue thinking of things. Much better to hear your voices than mine droning.
Sure,
on.
we've got a few. Arjun,
Go ahead.
Go ahead.
Arjun, what have you got?
Yeah. So I've got a few questions on asteroid detection because I like to do asteroid detection. And so I have a question, actually multiple questions. So one, how does radio asteroid observations compare with optical in terms of how is it detected and how hard is it to detect? And two, the last question is what sort of emissions does it put out? Like, how strong is it?
So, okay, to answer your first question, so for us, we don't detect the asteroid object first. So it's still detected optically. And we look at any number of these near-Earth asteroids that pass by our planet. And if it's of particular interest, then we will do these direct observations. And I'll see if I can find while I'm talking to you, I'll see if I can actually find an appropriate image. So I'll just what I'll do is I'll stop sharing that slide so I can come back to me, and I'll see if I can find a useful image to be able to show you. So what we find is with these, I'm going to try and talk and type at the same time. Doesn't really help. So it's found optically first, and then as I said, if it's of particular interest, we will then do these radar observations. So think of it a little bit like sonar that perhaps a submarine might use. We send out a radio pulse that then is reflected off, that reaches the asteroid, reflects off the surface of that asteroid. And what we do is we literally scan that signal across the object, just doing milliarc seconds of movement and being able to actually build up an image which then reflects down to another receiving station. And just to see if I can bring up a little image here, and let me share that screen again. This is where it gets fun. and share there. Okay, so you should see in that image there, this is one from the Goldstone Solar System radar. This is multiple images of the same object. And because we can scan it over many hours of time while it's in the field of view of that particular station, we can look for the rotation of the object. So we can see how this particular object is slowly rotating, tumbling over time. And it looks like we've got a sort of a day side and a night side. It's just the near edge and the far edge. We get to sort of a higher reflectivity of the radio signal. So we can sort of build up a 3D image of these objects. And from the received radio signal reflecting off the surface of that asteroid, you can actually build up a lot of more information. So depending on the quality of the signal that is received, we can be also looking at variation of composition, and temperature can be inferred from the surface of that object. So I don't pretend to understand the full science on it. It's not my specific area, but that's, it's quite remarkable that with these objects, which could be, many millions of kilometers away, to be able to build up an image like this. And quite often too, we can make this really interesting discoveries. A lot of binary pair asteroids that might have an asteroid like this, and it may have a small companion asteroid orbiting around it, a small moonlet. And the Deep Space Network doing these radar observations, the moonlet would maybe too small to be seen optically, but can be spotted in radio. And that was particularly important when the first observations were done of the asteroid Didymos with its small moon Dimorphos, which the DART mission crashed into last year to try to see whether we could deflect the orbit of an asteroid. Interestingly, if you've all seen the pictures of the coming from the cameras on the DART mission as it raced towards the surface of that small asteroid, smashing into the surface of it, all of those images were beamed straight to here in Canberra, and we were broadcasting it live, across the internet around the world. It was just a remarkable thing to be standing in the control room watching all of that happen. So yeah, that's how we do it. We build up images like this, bouncing those signals off. In terms of the signal quality, to sort of get to your second question, the signals we will do in that transmission is probably around about between, depending on the distance of the object, between 20 up to about 75 kilowatts. That's fairly typical. So it's quite a bit of power, concentrated beam being sent out to that object. The reflected received signal, though, is going to be in the order of around about something maybe 1 billion times weaker than the power generated by a watch battery. So, we can shout out and send that signal off the asteroid, but we're receiving a whisper. And I always find it remarkable that that tiny signal received at the receiving antenna can be enough, data collected to be able to build up these remarkable images of these distant objects. Let me stop sharing there and come back to that. Does that cover the question? I went on to a little bit long, but does that sort of cover it for you, Arjun?
Yep, it does. Thank you.
Cool. All right. And find out more about it. The Goldstone Solar System radar is a wonderful system. It's the first system created to do this kind of work. It's your own tracking station there in California, and there's plenty more you can find out about it through their website, and or just Google the Goldstone Solar System radar, and you can find out all the details about how it's done.
That's great. We've got one more question. Joseph? You're muted, Joe.
Okay. Yeah, I'm so glad that you came here to do this. You came here. No, you decided to help us with this.
I beamed in.
The thing is that you were talking about the Voyagers and the mission was extended. I think that was due to some, there was a result of helping the power system out, and they came up with a way to extend the power.
Yeah, they had to do a lot of conservation of power. So a number of instruments have been turned off over time. Obviously, the cameras were the first things to go off. So the literally TV cameras, they were sent long before we had digital. And they were the last image taken by the Voyagers was in 1990. That conserved a lot of power. we turned off one of the star trackers. We didn't need power for the thrusters anymore, so that was reduced. In fact, it was only a handful of years ago where they decided, hey, we haven't run those thrusters in 30 years. Maybe let's see if we can send a command and turn them on and see if they'll still work. And amazingly, they turned on and they still worked. So, great engineering of that spacecraft. But over time, yeah, the multiple instruments on the Voyagers have just been turned off one by one in sequence, continued to conserve power. We've reduced the heaters required for the spacecraft so that keep the interior of the spacecraft warm. We're literally just keeping the radio on now to generate its own internal heat, and we're talking incredibly low temperatures, but just enough to maintain the warmth to keep all the other instrumentation operating.
Yes, but Glenn,
amazed by the work's done.
Yeah, what I'm talking about is just last week there was an announcement by, I don't know if it was NASA or somebody, and just last week they came up with a method to get more years out of it. Yeah,
and that's again by reducing the power that's used by the spacecraft. So turning off the internal heaters and only keeping one of the internal systems on, and using the radio to actually generate, its own internal heat that it generates. Gives us that the instrumentation to still operate and to not be draining down the power from the radioisotope thermoelectric generator, the RTG, on the spacecraft as great a rate. So that has allowed us to extend the mission. So the previous plan was the last instrument would be turned off in 2025. Now with this little conservation of power, that is now extended to 2028.
Okay, so it was just the same kinds of things they've been doing all along then.
Oh yeah.
Okay, I thought it was something special in the power system.
Yeah, no extra power. It's just a matter of not keeping the spacecraft quite as warm as it was before, because again, the heaters, consumed a lot of power. So we're still losing about 3 watts of power every year, and we're the whole spacecraft at the moment is only operating on about 40 watts. It's about the power, like a dull light bulb you might have at home.
Well,
thanks a lot, Glenn.
Yeah.
Not to derail you too much, but
that's right.
Is it easy? Can you briefly describe what science it's still doing?
Yeah, so it's primarily looking at the high energy environment from the rest of the galaxy, which before the Voyagers left the heliosheath, really the dominant energy was the outward streaming energy from our sun. They traveled through the heliosheath, effectively like a wave, like a shock wave around the solar system. We saw lots of variation in that wave, the heliosheath boundary. And then eventually with the Voyagers, particularly Voyager 1 crossed the heliosheath boundary in 2012, and for Voyager 2 in 2019, if I recall right. So they're now effectively in the clear air of space, so they can negate basically the magnetic bubble of our sun and the outward streaming solar wind from our star, and now sort of in that clear air of the galaxy, be able to receive in the high energy environment created by all the other stars, the interstellar wind. They're also looking at density of the space environment. So for the Voyagers, they're encountering about 1 hydrogen atom per cubic meter of space that they travel through. So that's about as next to nothing as you get. Anything else that comes up, but basically more information about the wider magnetic field of the galaxy, and anything else the instrumentation can be utilized for. So Voyager 2 has 5 instruments still operating. Voyager 1, I think now is going to go down to 3 before the end of the year as they continue to conserve power out. And it is just remarkable that, we've got instruments which are designed in the 60s and 70s, designed for planetary observations, are now being used for interstellar observations. I think that's just, again, a great testament to engineering.
Thank you. That's amazing.
I was just going, well, if anybody's got any other questions, please ask. What I'm going to do is just run in the background, just some nice aerial shots of the site, because it's just a pretty site to look at. So let me just share that video in the background. There's no sound on this. And you can see again now some nice aerial shots that we did recently.
So you mentioned Pioneer. Pioneer is not talking to us anymore.
No, last time we had contact with Pioneer 11 was in 2002. So they have been silent since then. They literally have gotten so far away, their signal so small that it's now fallen into the background noise generated by the rest of the universe and radio frequencies. So a little voice lost amongst a very big crowd. The kind of signals we're getting back from Voyager transmits at about 19 watts of power. So about the power it takes to run the light bulb in your refrigerator. By the time that signal travels all the way here, the signal is spread out, becomes so thin and diffuse, the signal footprint is now larger than the Earth's orbit around the sun. So you're only at the big dish, as you can see there in the video, receiving at the receivers on that antenna, the signal is equivalent to 1/24 billionth, with a B, the amount of power of a watch battery. So for anybody technically minded, that's it's 3.4 times 10 to the minus 24 kilowatts. So a ham radio operator there, the other Glen, probably appreciate just how tiny that signal is. It's minus 160 decibel milliwatts, dBm.
Was Pioneer further away than the Voyagers, or it just was a different system and it didn't have as much energy?
No, just a smaller transmitter, lower power, and the spacecraft basically fell silent in 2002, just overwhelmed by the background noise. So it's probably still could still be putting out a very weak signal, but yeah, it's just the signal is overwhelmed by that background noise at about universe is at about minus 172 dBm, and that spacecraft would be sitting at about minus 150. So the noise of the universe is just something we'll never be able to break through to try to find the Pioneer, even if they're still capable of transmitting after all this time.
Thanks. One last question. I'm a big Apollo aficionado, and one of the places we always heard about was Honeysuckle. Where was Honeysuckle?
So Honeysuckle Creek.
Where is Honeysuckle?
Yeah, so the Honeysuckle Creek station. So originally there were 7 stations in Australia, 2 stations in Western Australia, 1 in South Australia, 1 in Queensland, and 3 stations here in Canberra. So our station here, obviously at Tibbinbilla, 1 at a place called Aurora Valley, about 40 kilometres south of us, and then a 3rd station known as Honeysuckle Creek, about 25 kilometres from us. And Honeysuckle was built specifically to support the Apollo missions. It was part of what was then known as the Manned Spaceflight Network. And the antenna you can actually see here at the bottom of the screen, and I'll just actually scroll along because there's another nice shot of it here. Yep, there it is. That antenna originally was at Honeysuckle Creek, and it is the actual antenna that received and broadcast to the world those first historic images of Neil Armstrong and Buzz Aldrin walking on the surface of the moon. It also supported all the rest of the Apollo missions. When after the end of the Apollo program, the Honeysuckle station joined the Deep Space Network, and we used the antenna for deep space missions for a while. And then eventually in 1981, they decided to consolidate the Canberra site. So Honeysuckle was closed, its antenna was dismantled, it was moved up the road and rebuilt here at our site. In fact, I look out my office window and see that dish every day. And for me, that's like coming full circle, because I was 7 years old when they landed on the moon. And I remember sitting at home watching those ghostly black and white images on the television and seeing Armstrong step onto the moon, and having no idea that, more than 50 years later, here I would be, sitting in my office looking out the window at the dish that brought me those pictures and started me on my journey in space, and space science. So it's an amazing thing to be a part of. Not only did that dish bring back that, one small step for man moment, but that dish was also the dish that was online at the time when the next most famous words in space history came along. You all know what that is? Houston, we've had a problem. Yeah. So that dish was vital in the first, 7 or 8 hours of that emergency with the Apollo 13 astronauts as well.
Thank you very
So
much.
yeah, a lot of
Fascinating.
history in this place. A lot of history.
Two more quick questions. Go ahead,
Yep.
Arjun.
Sorry. So I just had a quick question on the one more thing about the asteroids. So I was wondering, would it be more efficient to like detect the shape and rotation of an asteroid using like radio, or would it be more efficient to use occultations and light patterns using optical?
So you can do a little bit of both. Radio has a greater flexibility to be able to actually watch an asteroid over long periods of time and to see the darker side of it. So for optical, you can really only have what light is reflecting off it. So in the optical wavelength. So if you've got a part of the object that's in darkness, reflecting sunlight directly back to your optical, telescope, then it is invisible to you. So with radio, we're not worried about the optical wavelengths. We can basically build up an entire image of that particular object. And both, optical and radio go hand in hand. You've got to have the optical first for the observations. You can get a little bit of inferred size of the object from optical and so forth. But if you really want to get more detail in terms of the size, structure, rotational rate, composition, temperatures, range of things, then radio is definitely the way to go.
Okay, thank you. Yep.
I have a question. So I'm noticing in your video right now there's automobiles. There are cars driving around. Is there special provisions done to those to prevent them from emitting radio signals?
So no direct changes to the cars, but a lot of the work that goes on in our operations building is processing out the stray interference. So when we have all the different electronics on site, whether it's the lights that are on in the room that I'm in now, or the computers that are operating, or the electronics on the door locks, or the cars, then we have to basically have a good idea of you need to know exactly the frequency of that particular interference, and then in the processing that can then be nulled out. But for the high frequencies that we're generally working in, then the emissions from the cars are not really a problem. It's well below what we are actually using here. Where we get into more issues is particularly now with cell phones moving into the 5G generation of signals. That's starting to get right onto the edge of some of the frequencies that we use. So that's becoming more of a problem than that, say our cars or our plant and equipment, computers, etc. on site.
Thanks. Michael?
It's like getting rid of the junk mail, basically.
Another question from Michael.
Hi, Glenn. Yeah, I had a question more along the lines of cyber. So I work at Johns Hopkins Applied Physics Laboratory, and when we have missions that come up, I'm involved heavily with the defensive nature of our systems and networks from a cyber perspective.
Yep.
Given the global nature that the DSN has, do you guys find from a cyber, you may not know this, I don't know, but are folks kind of more or less hands off because it's a global initiative? Like, hey, we're interested in things from a planetary perspective, or no? Similar to what we do is make sure that we're ready for some, actor that may be coming at us in some perspective to hit us at a moment of, oh, we're about to reveal DART, right? Like we did that at the laboratory.
Yep.
What kind of happens there? Is there a huge IT and cyber defensive force supporting your specific site?
Oh, we have an absolutely huge force of one person.
Oh, wow.
So the network itself is primarily connected back through the Jet Propulsion Labs, and they certainly have, quite the team there dealing with cybersecurity. But you can get attacks at the site level. And so our cybersecurity person here has set up a really excellent system, works very closely with our colleagues at the other stations, and to keep an eye on individual attacks that might be directed specifically towards the site. We've never had an intrusion getting in through even we have multiple firewall systems. I can't go too much obviously into the detail, but yeah, we've never had a successful attack through there, but there are lots of bad actors around the world, in lots of different nations, and who try. But so far we've been exceptionally lucky from the site level. I will relate a funny story. The one time where we did have an intrusion, it was kind of internal. There was back when the Curiosity rover was due to land on Mars back in 2012. Yep. It was a very anxious moment for NASA and JPL, because a lot rode on that mission. It was using the sky crane maneuver, which everybody thought was crazy. Will it actually work? If it had been a failure, it could have been a big problem for the agency ongoing. It was a critical time in funding and a range of other things. So there was a lot of anxiety about it. And I think a couple of people on the mission, while we were, we were the station, the prime station, handling the communications for the landing, and two people working over at JPL decided, oh look, we're nervous, we want to know what's going on. And so they actually kind of went in through a little back door to sort of monitor what we were doing and our systems, and our system saw that as an intrusion threat and completely shut everything down. It was seen as if there'd been multiple, gotten through all the multiple firewalls and gotten directly into the system. So to protect itself, the system shuts itself off completely. And so, your control room went suddenly dark. This is about 2 hours before landing was due. So it was realized very quickly where it came from, that it was not an exterior threat. It was just a couple of anxious mission people wanting to know what was going on behind the scenes.
Whoops.
So yeah, whoops. I think they probably got a talking to, but yeah, I'll put that into my book. I'm going to write a book about the network and some of the fun things that have happened behind the scenes, and that'll be a chapter in the book, I'm sure.
I'll buy it.
We've
gone way over time, haven't we, Victor? Yeah.
Yeah, we just have a whole bunch of questions. So there's two in the chat, and then Phil has one.
Okay.
Are you okay? Do you need to?
Yeah, I'm fine. Yeah. I've dedicated this time for you. Yeah.
Phil, you want to go ahead?
Sure. Glen has Starlink. Is that causing any issues, or is there an agreement that Starlink will not fly over?
Oh no, they fly over. Again, they're not such a problem. They're at a lower frequency than we're using. It's kind of more the other way around. We have to make sure that we're not transmitting when you've got Starlinks and any other satellite overhead, because while a signal's moving at the speed of light, and it's usually very, very short pulses for transmitting commands to spacecraft. But we have to make sure that there isn't a satellite overhead, because at the power we're transmitting, and depends again on the location, it can be 8 kilowatts. We have a 100 kilowatt transmitter on the antenna. That would take out the electronics on a satellite. So we all our coordination of that, we just have to make sure that they're not under threat by us. So if you want any Starlinks taken out, we're happy to do it. No, we're not. I didn't say that. I said that out loud.
We'll let you know during our next Star Party. So.
Yeah, we actually just on Tuesday this week here, myself and my colleague attended an event with the Australasian Dark Sky Association, and trying to protect the night skies for astronomers and also for radio astronomers. So there was a lot of discussion going on about Starlink and all the other mega constellations that are going to be thrown up there over the next few years. So, the Chinese are looking at a mega constellation with over 130,000 satellites. It's going to get busy, really busy up there. It's busy enough now.
That's insane. Is it gonna make it so that you can't even ever transmit? Are you?
Oh no, we'll transmit. Don't worry.
Okay.
But look, it is a problem, and something needs to be addressed. There's not enough regulation going on that. You get all these entrepreneurs out there, wanting to create these worldwide, broadband communication systems for internet and other things, and lots of other nations who kind of don't work as cooperatively with the international community as we'd like. So it's something that needs to be addressed. We really need sort of a worldwide effort to protect the skies, to reduce the risk of collision, most especially because you get a mass cascading event, and it would be a real problem. It would actually to take out communications and observational satellites, and the International Space Station would be more under threat, and even just launching a rocket, is going to be harder and harder if we don't deal with this issue of space debris and these mega constellations. There needs to be more regulation.
Sure. So we have a question from the chat. Ben, who has no audio, would like on his behalf for us to ask you if you know Dr. Steve Nerlich, the astronomy podcaster.
Yes. Yeah, absolutely. Steve used to be one of our volunteers here in our visitor center for many years. So we know Steve really, really well. He does a great podcast out there. It can be a small world, the astronomy community. Sometimes we all get together online, even though there's lots of us everywhere all over the planet.
Yeah. Well, if you're ever in the Washington, D.C. area, you're welcome to come to a HAL event. Speaking of being a small world. And we have another question from Mark, posted into the chat. What backgrounds and skill sets and degrees do people working on the technical systems at these radio astronomy sites typically have?
So you can't go off and do a university course and get a degree in deep space communications. So not yet, at least. So what we do is we tend to find people have good aptitude and attitude in their particular areas. So if we need mechanical or structural engineers or electronic engineers, electricians themselves, or people with skills in HVAC systems, for high power and air conditioning, and or if there's people who are carpenters, if we really just find people who are good in those areas and bring them in and then train them up to our standards. So kind of my advice to Mark is kind of find something that you love doing and try to be the best at it, and particularly if you've got that good attitude too. I think that's really important, because it's always important in the space community, no matter what that area is. Good communications, good, getting along with people, working as a team is really, really critical, because we're all reliant on each other. We work long hours. We could be here at 3 o'clock in the morning on Christmas Day fixing something, and our people come in and no complaints, come and do it because they love what they're doing. So that good aptitude and attitude, really important. Love people who have an interest in space. You don't have to be, but it's nice to be working at a place where you go, hey, there's that wonderful picture from the James Webb Space Telescope. I was involved in helping get that image to Earth, and getting it out to the scientists. And so, yeah, a lot of our people on site, engineering backgrounds, electronic backgrounds. I've got a bunch of people in our control room who used to be former, naval radio operators in their earlier careers, and they have brought skills to the job. So yeah, it's interesting, the wide range of people. We actually here in Canberra wrote the manuals on how to do the operations control room stuff, the communicating with the spacecraft. We actually train our colleagues at the other two sites now how to do this sort of stuff. I think it has to do with the fact that we're a really remote nation from the rest of the world, so we've gotten really good at communicating over really long distances, including deep space.
Terrific. And if you don't have those people skills, then then you try to get the job out in Western Australia where there's only one person,
Very few
10
people.
kilometers.
That's very true.
We are kind of getting low on time, but there's one more
Yeah.
question. Joe, you want to ask your other question?
Yes, I would. I was wanting to bring up the fact that any amateur astronomer with a decent telescope could do near Earth object viewing. And the NASA Astronomy Club is doing some of that now. And I think one of the members belongs to the Howard Astronomy Club, which is John Nagle. Him and Kevin Hartnett, they both work on that. And there's an organization that they joined that puts it all together and tells you when a particular asteroid will be at what RA and declination and when it's going to pass through that spot. So you kind of just look through that spot and you pick it up and you provide the data that you get to this organization, and they make a determination as to how it's rotating and the size of it and things like that.
Yeah, the amateur community has become exceptionally important to near-Earth asteroid observations. There is not enough professional astronomers in the world whose job it is to, just scan the skies for those kind of objects. And we've had certainly space telescopes like NEOWISE and others that, scan the skies. But it's quite often now the amateur community. I know here in Australia there is actually less people, keeping an eye professionally on the southern skies, that are invisible from the northern hemisphere for near-Earth asteroids, than say the number of people that might work at a McDonald's store. So we need a lot more people, and the amateur community is extremely important to doing that kind of work. And the more observations we get, the more information we can build up. Certainly more information, more observations over longer periods of time, because a lot of time is spent by the professional community. Something gets spotted and then they've got to go back through all their optical observations of that similar region of space to see if they can backtrack where that object has been in the past, so that they can then determine, that the orbit of that object. So, the more we can get the amateurs out there and doing the observing and building into a database, all that information, the safer we're going to be here on planet Earth.
Thank you.
Well, unless anybody has any other questions, I'd like to thank our guest. Were you done? Any other slides that you were?
Oh, we could talk for the next couple of days. I've got so much I can show. But anyway, I'm always happy, to come back and chat again if there's any particular topic on a mission or something that you're interested in. So much happening with the James Webb Space Telescope at the moment. We're preparing for Artemis 2 next year for that first crew to return back to lunar space in more than 50 years. And that's getting really exciting. We've been doing major upgrades on all our antennas to be able to support that. Getting back into human space flight again, which is really exciting. And, I'm sort of hopeful that next one small step for humanity might be also coming through an antenna here in Canberra, and we'll get it to beam out to you live around the world.
Terrific. I would like to stay in touch, and maybe we can discuss something like that going forward. But other than that, I'd just like to say thank you so much. This was an amazing talk. If everybody can,
thank you.
Much appreciated. I guess I'll just go ahead and share my screen and continue the rest of the meeting then.
All right. So Victor, I'll step away. Thank you all again very much. It's great to see and talk to you all. And Arjun, are you going to become, a space, one of our space communications people or an asteroid observer in the future?
Definitely. I'm actually more interested into like spectroscopy and asteroid mining. So that's something I want to get into in the future.
Perfect. I will see you out there in the universe.
Yep.
Maybe,
All right.
maybe you should be an astronaut and go to an asteroid June.
Yeah.
Yes, we will see. We'll,
All right.
that's a
And
possibility.
I wish all of you clear skies.
Thank you so much.
Yeah, thank
Thank you
you.
very much.
You don't need
Thank you.
them, but we wish you clear skies too.
It's beautiful out there at the moment. All right. Thank you
All right.
very much. And thanks again for inviting me.
Sure, thank you. Okay, so moving on, we've got a couple of we're back to Phil with talking about what's going on in the sky with the sun these days.
Thanks, Victor. So tough presentation to follow there. But I have to tell you that as we move into this particular section of the meeting, that we have a lot of astro imagers and we have a lot of people that have the potential to see and discover things with your images that, you know, as you're processing them, that you may not have noticed before, which is truly exciting. And that's exactly how a guy in Germany who was an advanced amateur, you know, he imaged the first ever supernova as it was happening. And that was an amateur, not a professional. So, you know, I always tell people that we meet at our star parties that astronomy is the last science where an amateur has just a good chance of making a discovery as a professional does. You can't do it in oceanography. You need millions and billions of dollars. And other sciences, you need all this equipment, but with, you know, we could see things with what we do. And the reason I'm bringing that up is because I'm going to talk to you in a few minutes about something we witnessed just a couple of weeks ago. And I'm going to come back to that. So that's kind of a tease. But I do want to talk about, you know, it's no secret to anybody here how we're in a ramping cycle of the 11-year solar cycle. We're in the ramping stage. But this solar cycle is way more active than it was in the last solar cycle, and really even in the solar cycle before, which is really great for observers like myself and those of you who enjoy observing the sun. But it's really troublesome for all kinds of other things, including the astronauts on the space station, the satellites, the communications network, the power grid here on Earth. You know, you could see that almost every day there's a news story with something that's coming on related to the sun. I don't remember ever a period where the sun was making the news almost every single day. So here's just some highlights, you know, that I put up there. You can see what's going on. Victor, if you want to hop to the next slide, please. So here's an active image. You see where the peaks are, and you could, you know, as you're looking at 2023 there, right between 2022 and 2024, and you could say, well, you know, hey, that doesn't look much more active than it was back in 2015, or getting close to 2015, except the fact of the matter is that this peak in activity is years, you know, at least 2 years before the solar peak happens. So that other one was the solar peak. And you could see just how quiet it's been basically since 2018. All the way through for solar observers and stuff. It was really kind of boring. We were pretty excited when a single solar spot showed up. In the last 2 years, you know, if you look at spaceweather.com, they always have a chart on there that shows how many days have gone by without at least one sunspot. And if you look back over the last few years, you know, 1 year it was over 200 days without a single sunspot. Now in 2022 and 2023, there has not been one single day without one, at least one. So it's quite active, and it's going to get more active. What I find interesting on that graph there is you look out past 2023, where the prediction curve is, whoever did the prediction curve, which is called the CM predictions, which is the thicker dashed line coming off, it's showing that dropping off completely, where the SC predictions are showing it going straight up. I don't know where that CM prediction model is, but it might be our local weatherman who just doesn't get it right. So that would be a tremendous pivot to the trend right there. So this is what we're looking at right now. Next slide. So here's what I was talking about. You know, many years ago, actually it was a decade ago, I didn't have any HAL people with me, when I witnessed Morton waves, which is a phenomena that's almost never seen. But there's no question that's what I saw that day, and I had nobody with me when that happened. One is to help validate that's what we were looking at, that's what I was looking at. And the other thing was to share in the excitement of it. This was not true. So 2 Saturdays ago, on May 6th, at our public outreach where HAL was supporting an Earth Day event, which happened to be held at Clarksville Commons in Clarksville. And there was a really nice turnout of the public. You know, they were there for all kinds of activities, and we were there. That picture up in the right shows in a panoramic view of our setup with the solar setup, the table, and you know, Gary Richardson was there, and Arjun and his family, and Bob Savoy was set up with his telescope and helping people with education, and other people were coming in and out. And I had stepped away from the telescope and asked Gary to watch my scope for me while I stretched my legs for a few minutes. And he came running over, and Joel was there, also Joel Goodman, and he came and got me, and he said, "Phil, you're going to want to see this." So if you look down towards the 4 o'clock on the sun there, maybe Victor, you can run your cursor there. This is not my picture. We had no camera setup or capabilities. I forgot to even bring my cell phone adapter for the scope with me. But there was a tremendous explosion, which I thought was a CME happening. I was convinced in my own mind it was, but when I went back and I've done the research afterwards, there was no reports of a CME, even though there was 2 that day, but none was reported right there. But this was the largest single event. I've been doing this since 2012 with the H alpha without missing. You know, I've been very active in it since 2012. And I've seen some very cool things happen. Remember, the sun is only about 8.5 light minutes away. So it's about as close to real time as we're going to see in anything astronomical, except for the moon, right? And but not much happens spontaneously on the moon, because that would really be a newsmaker. And this giant explosion showed up here, and it just got bigger and thicker, and then it was dissipating just as fast. And what I've done here, this picture was actually taken by, full credit to the NASA Solar Dynamic Observatory, which you see there in the bottom left. The data you can see when it took place was at 11:27, 43 seconds of our time here, Eastern Daylight Time. And the total duration from beginning to end was 2 hours. And that was from the time it first showed up, from a little blip of explosion until it was completely 100% gone. But the whole event, as far as was less than an hour for what we really saw was cool. So let me put this in perspective for you. So if you can push down arrow one time. So what you see there, this is the scale. It took me a long time to put this together. That's actually 110 Earths. So the sun is 880,000 miles in diameter. The Earth is approximately 8,000 miles. So it's 110 Earths to fit across the sun like that. So there's the scale. So that's there. Now, here we come. So you see that explosion happening right down there on the and you see the Earth relative to the size of that, to give you a humbling experience of just how massive this thing was. If you do the next one. So to give you an idea what that means, from in that arrow there, from what we'll call the surface of the sun to the farthest most edge in this particular picture, is 220,000 miles. I stepped it off, so I know that. I walked it off. So if you do one more, Victor, and then you can see from that one end to the other is approximately 100, it's probably closer to 110,000 miles right there at that moment. So this is really, was so cool to watch. And it was so cool to watch, I could tell you that somebody was so excited by what they saw. I didn't know this at the time. I found out later that day because I got a phone call from Marty Cohen over at Company 7. He said, whatever you did, Phil, there was a person there who looked through your telescope, saw all this happening. He ran over and he bought a 60 millimeter Lunt H alpha scope, a mount, eyepieces, and everything else. He ran right from Columbia, Clarksville Commons to Laurel to buy his solar telescope because of what he saw there at this moment. Next slide. So I went to the Big Bear, this one's not from Big Bear, this was actually from Solar Dynamic Observatory. This was the video that was taken by them, and this is like 24 hours of video. Watch carefully when this blinks by to show you how fast it happened. That was it. So Victor, if you could just kind of slide back from the back end, run it, yeah, one more time. There you go. That was the whole thing. That was about 2 hours. But if you start at the far right, Victor, and slide, you could stop it and you could just kind of crawl it across. You'll pick it up at about 16:30. Go back to the right. Just put your cursor on the edge of that or pause and pull it right and left. There it is. And if you go slow, you could see it happen. That was so thick. You have to understand the excitement, everybody, as to how cool this was to be looking at this live through the 60 millimeter H alpha telescope. I mean, the people from the public, they were amazed. And Joel, Joel, Gary, you guys were there if you want to pipe in.
I could pipe in because I showed up.
Well, yeah, Victor, you were there too.
I showed up right then. That's when I showed up. I saw nothing. But what I did see was how excited you were, which was fun.
Yeah. And Gary made the first discovery because Gary, maybe you want to say you looked 1 minute, it wasn't there, and the next minute it was gigantic.
Yeah, I was just every, 10 to 15 minutes, I was just peeking through the eyepiece because there was so much going on the sun. It was just fascinating to watch. And I just happened to wander over and look through the eyepiece and saw this enormous explosion that had not been there 10 minutes prior. And so I suspected that Phil would be interested in it. Immediately ran over to get him. And by the time Phil got back to the scope, it was probably 70% of the size that it was when I had just seen it a few minutes earlier. It happened so quickly.
Yeah.
Has anybody calculated like what's the like how fast, like 220,000 miles in 10 minutes? I mean, that's some pretty fast moving particles there.
Yeah, it was. So in those explosions, the radiation is traveling at the speed of light. But the ionized plasma is moving much slower relative to the speed of light. And if that was an Earth-facing event and it launched all that plasma towards the Earth, it's going to take about between 2.5 and 3.5 days to reach the Earth, depending on the speed of that particular blast, which is still pretty darn fast considering it's 90, on average 98 million miles away.
That's just amazing.
But it was so cool to witness. And this is one of the greatest things about solar observing is you see things happen and you could watch them change as you're observing. And the scale is huge. So it's kind of looking up in the sky and seeing an airplane that's 30,000 feet up in the air, or 30,000 feet up in the air. And it looks like it's just crawling across. But if that plane was, 500 feet off the Earth, you would feel the 600 miles an hour, 600 miles an hour that it's traveling at. And, so when you look at the scale there, to see something move and you could actually see it moving, it's just incredible how fast it's got to be going.
Well, the math is pretty straightforward, right? If it expanded from the surface of the sun by, call it ballpark 250,000 miles, and there's no way it took 30 minutes for it to reach that distance. It was traveling at over 500,000 miles an hour.
Yeah.
Awesome.
It was so cool. And these are the things that, it's just how much do we miss that we never get to see? And you could just look at the reports from space weather or whatever. You could see if you happen to be observing at that time, you have the ability to watch it happen.
Yeah. Well, your excitement rubbed off on at least one person who went over to Company 7 and picked up a film.
No, so it was truly exciting. But that's it for this month.
Thanks. Jim, do you want to talk about Shallow Sky?
I don't know after that.
I have a question for Phil.
Oh, sure. Go ahead, Joe.
Hey, Phil, how do you do your observing? Only with your naked eye, or do you have a camera that you look at it through the house, in the house?
I do a lot of optical observing. The beauty of doing the imaging in the daytime is you're shooting at very high rates of speed. And unlike when you have to let the telescope go for deep sky imaging, where you're gonna have to let it run for hours at a time or much longer to capture the beautiful pictures we see from the gang here. With the solar stuff, you're shooting at totally high speed, so I could
But you're
shoot.
doing video. You're doing video, or are you just taking a picture every now and then?
So both.
Okay.
So what I'm gonna do after this experience is I'm gonna set on a clear day, I'm gonna set the telescope outside my house and, figure out how much viewing time I have before the trees or something gets in the way. And I'm just gonna have it take a picture every, few minutes, or run video for several seconds every few minutes, and then build a time lapse myself, just like is done in the real world for the professionals. And but normally when I shoot, I like shooting in TIFF. I get a ton of data and I don't have to capture a lot of fields. And that was why when I do my pictures, I just have tons of bits to work with. So I do both. But the thing is, I could get my imaging out of the way in just a few minutes and then visually observe the rest of the time. So
So
I missed
could-
the
I
opportunity.
have another question for you, Phil, and I think you're the guy to answer this question. There looks to be waves on the sun. If you see that one wave near the top, it's kind of going from light to dark, light to dark.
Yes,
That one is showing a ridge around the circumference. Out to the left of the hand there,
right. So
right there, yeah.
yeah. So what you're looking at there is called a filament. We're looking at it at a hydrogen alpha viewpoint at the H alpha bandwidth, which is 636 nanometers.
Yeah, I know what a filament is.
Yeah,
I've
so what
through
you're
a lot
looking
of H
at, you're
alpha.
looking at a filament, which is exactly the same thing as when you look at the prominences coming off the edge, the ones that stand. I mean, this was a giant flare that we just saw, which is a verb, but when you see these things that are hanging out there called prominences, the filament is exactly the same thing. So because we have pretty much a 3D almost view here, you could see the depth and the structure because it's all gas. It's not like looking at the moon and it's a mountain range and things like that. This is all gases, and you see the plasma here. So that's what's giving these things. That's what's showing all these features here. So that's what you're looking at. I hope I answered your question.
Yeah,
Addressed it
thanks.
properly.
Thanks a lot.
And spoiler, I've got a photo of Phil's coming up in the Astro Photos section, so maybe he can talk more about it then too. There's one of Phil's photos and how he captured it. All right, so moving on, if anybody has any more, if nobody has any other questions, we'll go on to Jim. So Jim is going to talk about shallow sky, i.e. not deep sky.
Yeah, so we don't have anything as exciting as what's going on there with the sun, with its activity, but we do have things that we know are going to be happening. And right now, our sister planet is really in a great position for observing for us. It's really high in the sky after sunset. It reached its greatest distance back on May 8th, where I think it was actually setting close to midnight, which is really pretty late for Venus to be setting. So anyway, from between now to our next meeting, the phase is as it's heading to pass between the Earth and the Sun, its inferior conjunction. The phase is going to go from 55% down to 43%. So a little bit bigger than a first quarter looking moon to a little bit thinner. But it also is increasing in size during that time. So it's going to grow from 20 to 27 arc seconds. And that at 27 arc seconds, I think that's about, aside from Jupiter, the largest that a planet is going to look. So it's pretty good size. So,
Wow.
And as always, catch it after sunset. Close to sunset, you sometimes get some nice stability in the atmosphere, and use a filter to kind of knock down the glare if you're doing visual observing.
I'm really looking forward to. I'm guessing you're going to be photographing that, and I'm looking forward to seeing what you
Hoping to, if the weather
Yeah.
cooperates. Mars is up there too, in Gemini. The other night, they were pretty much lined up at Castor, Pollux, and Mars. But it's really small, really difficult even for imaging. So other than kind of saying it's there and admiring it, there's not a whole lot going on with Mars. Next one. Saturn has come back into the sky, but it's you got to be an early bird. It's rising at about 2 a.m. So by the time dawn comes around, it's usually in a good position. It should be high enough to get some pictures or some good viewing if you want to take a look at Saturn. And again, if you looked at it last year, you're going to see that those rings are beginning to close up. And I think next year they're going to be very unimpressive. So you might want to catch it now. Next slide. Oh, Jupiter. Jupiter is just coming out of the morning twilight. Hopefully we'll beginning to next month get to see some more of Jupiter, but again, very early morning target, not well placed.
And this year, Saturn and Jupiter are both going to be a little higher in the sky than they were last year, I believe.
Yep, they're climbing out of that zodiac basement for us, which is good for us Northern Hemisphere guys.
Hey, Jim,
Yes.
did you see the occultation of Jupiter?
This morning? No, I did not. Probably
Well,
my
I think
Easter.
wasn't it yesterday morning?
I thought it was this morning. It was either this morning or yesterday morning. I saw posts on cloudy nights with some guys out west that got good pictures of it. But no, I didn't. My Eastern horizon is lousy, and my telescope is not really transportable. So I wrote that one off. But if anyone wants to see that, go on cloudy nights under the Astro Imaging Solar System Imaging. I think they call it Major and Minor Planetary Imaging Forum. They've got some very nice shots there of Jupiter slipping behind the edge of the moon.
Oh, thanks. I'm going to do that.
So one of the things that's going to be kind of fun coming up is that the M44, which is an open cluster called the Beehive in Cancer, it's one of the two clusters that is very close to the ecliptic. And so since it's near the ecliptic, it will occasionally get visitors from our solar system. And so on Mars, June 2nd, Mars is actually going to be embedded within the cluster. So that's going to be very cool. And then click again, Victor. Venus is going to hop in there on June the 13th, but Venus is going to skim it. It's not going to actually go through it like Mars is. So if you're new to observing and you're kind of wondering, hey, where is M44? What is this Beehive cluster? Those 2 evenings, you can use those planets, which are obviously a lot brighter, to kind of point you right to where the Beehive cluster is. And
Right.
you can click again. If you are into photography at all, and you really can do this with, you don't need a big telescope. I would recommend binoculars because you're not really going to see the Beehive without binoculars, but anything from binoculars and up would be great. And this is a wonderful opportunity if you have a camera, even just on a tripod with a telephoto lens, or if you've got a fancier setup, documenting. I think the one with Mars is going to be probably the more photogenic one, even though Venus is going to be more brilliant. It'll be closer in range to the stars, the magnitude of the stars and the color. So I think that one's going to be the more photogenic of the two, but either one would be kind of cool to watch.
That's awesome. That you're getting me excited.
And finally, can you catch the Schroeder's effect? So the phase of Venus, it appears very slightly concave. It's not a straight line when the Sun, Earth, Venus geometry indicates that it really should be exactly half illuminated. And we call that particular phenomenon dichotomy. So when Venus is like exactly half illuminated, that's dichotomy. And basically Schroeder was the first person to notice over 200 years ago that, you know, according to the calculations, it should be happening on this date, but it's like not. It's like, you know, that the line is either a little bit convex or a little bit concave. So go ahead and click again. We've got dichotomy scheduled for June the 3rd. So if we happen to have clear skies that night, or even a day or two before, get out your scope and see if you can notice any deviation from that perfect half moon phase, either visually or by imaging it. And again, you're not going to need a really large telescope. You know, it's 27 arc seconds. So, you know, even like, for example, my 80 millimeter refractor, I'm sure would be able to pick up put a little magnification on it and check it out. See if you can see Schroeder's effect that he saw over 200 years ago.
What is it that causes that? Do we understand?
I don't, it's still, I think, a little bit open for debate, but I think they're thinking that it's the way that sunlight hits the clouds, that it isn't exactly an even terminator. It's not like a hard lunar surface terminator.
I see.
But, they've got a couple of papers out there talking about it, and I don't think I've seen anything that's like really nailed it definitively. We've got some theories, but I don't know that it's specifically defined in terms of what's causing it.
That's really cool. Thanks.
Yep. You're welcome.
Okay, well, we only have a few. I think the skies have not been very cooperative, so we'll just go through a few Astro Images because we're getting short on, we've actually met our 2-hour time here. So real quickly, we'll just go through a few of these and guess who's up first?
Okay. So this is some of my images of Venus, again, kind of grabbing those with my 10-inch scope and soon after sunset. The left-hand one is in infrared, which sometimes you can pick up a little cloud detail. I've not had any luck with that yet, but the UV is really working out pretty well. I have a UV filter, and that is definitely, which is exciting for me. The first time, this is the first Venus apparition that I've been able to do this, picking up some of the cloud details, and especially a lot of folks, that southern cusp cap there is really, when I say prominent, it's a subtle feature. So, but people can visually, especially if you have like a violet filter to really bring out the blue kind of upper part of the spectrum. Some people can see that visually as well. So, if you're looking at Venus, look at that southern area and see if you can see that cusp cap. But the UV filter is really working out well for me. I'm really happy with it.
That's awesome.
Hey, Jim.
Yeah.
I noticed you're using a 10-inch f6 Newtonian. And the question I have is what kind of a mount do you have that on?
I have it on a Celestron CEGX L. It's a pretty hefty mount because I needed something pretty strong to hold that guy.
Yeah, and how much does that telescope weigh?
Haven't put it on a scale, but I need 2 people to mount it onto the mount.
Yeah, no, my telescope weighs 33 pounds. And I'm pushing the limit of the Atlas EQG.
Yeah.
But it's still working fine as long as I twist my telescope on each axis to spread the grease around. I found out that was a trick I've learned, and it still seems to be working.
Well, you're right. That's pretty good for an EQX there for doing that. But yeah, you got to have a good mount. If you don't have a good mount, it's not worth it.
Right.
Gene, are you still on? I know. Yeah, Gene's here.
Hopefully, can you hear me?
Yes.
Great. Okay, so this is was a total eclipse last month from Australia, and I was on a cruise ship, so I just had a telephoto lens. But this was what I was able to pull out to get. I was more watching it than trying to take pictures. And everything happened very quickly, so I didn't get a whole lot of pictures, but it was really cool. It was a short eclipse, which means the moon was not that much bigger than the sun. And there were a number of prominences around the edge, and they were really bright, and you could see all of them the whole time. And it was different from some of the other eclipses where, it's like first you see prominences on one side and then on the other.
That is spectacular. What kind of lens did you have? What size? What
is a 300 millimeter f4 telephoto?
Wow. 300 millimeter f4. That's awesome. That's awesome. Did the cruise give you glasses to did they give eye protective glasses? Did they know it was coming and prepare?
Yeah. The cruise was advertised to go see this.
Oh, I see. Okay.
And they anchored so that, right in the right place. And yes, they gave everybody glasses.
Okay. I didn't know if you were just on a cruise and you happened to.
No, they gave you. They went right to where it was supposed to be.
They give you Mickey Mouse ears and glasses.
Yeah.
Oh, that's amazing. And this one also.
Yeah, so this one is a lot shorter exposure, and it was also, the eclipse had actually ended where there's just a very thin edge. But yeah, you could see that, especially on the left side there's this huge prominence, and it was really bright. As I kept thinking the eclipse was over because the prominences were just so bright.
Maybe that was
The
the
other
same day that Phil saw that same action.
No, this was April 20th.
on
So
SBO.
Well, that's gorgeous. That's the this is what they call, is this what they call the diamond ring? I guess you're around the diamond ring moment.
well, just the diamond ring is really like the first little speck of brilliant sunlight that comes out, and this was like 10 seconds after that.
It's amazing.
The diamond ring is a flash. I mean, it's in either direction. So,
Bill, you got another one?
yeah. So this is a picture that I took with that 60mm telescope. And I finally, figured out how to use the color camera and get it set properly. This is not artificially colored like all my other ones previously have been. Although I did have somebody tell me I should. This is the color from the red H-alpha filter. And somebody said, well, they didn't like the red. They wanted me to change it to something more yellow green. And so that's just the artistic part. But what's fascinating, this was done with a 60mm telescope with a short, an Orion 2X Shorty Barlow on there. And the detail and the depth that was able to capture, it didn't have anything dramatic happening off the edge. You see those prominences, but once again, even that small loop prominence on the top, you could stick the Earth right in that hole there, even though that looks so tiny. But to see the size of these filaments, these dark lines on there, and the shape, and also Victor, if you bring down more towards the center there, the sunspot right down to the right of where you go to the right in there, the black sunspot. You could see how the magnetic fields are twisting around. All that plasma is being affected by the magnetic fields, and it looks very much like what you would do with iron filings and dropping them on a desk in a science lab when you were in middle school, and watching how magnetism works. And you could see this around so many different features, how the magnetic fields are affecting the plasma. And it is so cool to study while you're watching it. But this picture is just one of my favorites because of the depth. And you can see the bright white areas are plages. And one more time, and I'll let you move on, Victor. But if you go to the far left of the edge there, we see that those small prominences there, those are magnetic fields that are about to connect. They would continue from here to move up and over towards each other, and they connect. And when a magnetic field breaks is what's one of the things that causes these giant solar storms, because it releases so much energy and spews it off into space. But when they connect, they also release all this energy, and it works very much like when you study atomic science, with atoms, and how electrons jump from one level to the other, and it releases a photon and these kind of things. And this is just at a tremendous level, and it's so cool to watch actually happen. If I would have taken an image a few hours later, you would have seen a complete change in the shapes of these things. So that's my shot.
All right. Well, I think we're gonna wrap it up. I had one more astro photo because we had so few this month. I put in my guy, and the only thing I'll say about this is that unlike the photos you were just looking at, Phil's, and that were very short exposures, this was about 100 minutes of H-alpha and 300 minutes of regular light taken from dark skies in Western Maryland in March of this year. Phil, you were out there camping. We were out together in dark Western Maryland when I took this picture. So anyways, I like this picture because I got some of the IFN, this gassy stuff in between. It was dark enough to get some of that stuff in the picture. So,
Yeah, that came out good.
thanks. Yeah, that's what.
How dark was the sky out there? Did you see the Milky Way?
It's, oh, easily, like horizon to horizon. It's Bortle 3. And the Milky Way was, yeah, this is about 90 minutes west of Alpha Ridge, where we were. It's near the town of Little Orleans, Maryland, near the C&O Canal out there. So stay
So you
tuned.
were near the Potomac then?
Yes. So we still haven't figured out how to do it, but I want to see if we can have a remote star party to go out to one of these dark sites one of these days with the club.
So what are we looking at?
This is, oh, I'm sorry, this is M81 and M82 and NG. So this is Bode's Nebula and Cigar Galaxy. Obviously, it's not really a nebula, but it was, you know, when it was first discovered, it was just a hazy patch. But this is 12 million light years away. These two are interacting, these galaxies, and it's causing this starburst effect due to the gravitational impact. It's causing all sorts of hydrogen gas to.
Yeah, that is incredible. It was the third thing that was throwing me off.
This guy here.
Yeah.
Yeah, I forget what he is. He's an NGC something. But yeah, it's
incredible. Incredible.
Thanks. Not actually, if we're talking about it, here's one last thing I'd like to point out, is that these guys are 12 million light years away, but there are all sorts of little galaxies in the background here. Like here's one, here's one. There's this image is chock full of, you know, 400 million light year away galaxies, like right here, here's one, a little hydrogen alpha region there. So
really, it's absolutely incredible.
Yeah, it's a pretty amazing part of the sky. So yeah, if you have dark skies, you can get some nice stuff to come out. And
Tell the secret, you know, when you're sitting there with the camera running all night, bring somebody with you that has a telescope with an eyepiece and our night vision device even better.
That was the best part about that night, is while this thing was off doing its thing, Phil was treating me to some very nice views with his scope, and his night vision thing too was amazing. So okay, I think that's all we have. We're over time, and thank you guys for coming. I don't think Crystal ever made it, so we'll talk about the book of the month more in more detail next time. And again, thank you guys for coming. Arjun has one last thing you want to say, Arjun?
Yeah, I just wanted to mention, I don't think there were a lot of people when I said this, but on Saturday there's gonna be like a children's business fair, and there's gonna be like a lot of child-owned businesses there, and I want to be selling my paintings. I'm also going to be representing HAL there. There's going to be like a lot of interviewers there, and I want to share my passion for astronomy. And I'm also selling a lot of space art, and I think a lot of you guys might like it. So yeah, I just want to put that out.
Let me stop the share, and then maybe you can give some more details. I'm gonna stop recording now. Did you say where that was?
Yeah. Oh no, I didn't. It's actually going to be at Columbia Mall.
Okay. When exactly?
This Saturday.
This Saturday, what time?
1 to 4.
Okay.
Make sure you send an email out to the HAL group.
Sure,
Just
I'll
write it before you send, make sure it reads clear and
Yep.
with the directions and the time, and you're gonna get a lot of friends showing up, I'm sure.
Yep. Thank you. Yeah.
Hey, you know, Victor, I do want to call out, you know, at these events, you know, Bob Savoy is, you know, just tremendous always to have as part of this, you know, with the table and everything he does. And Joel is, you know, is an icon at our events. You know, he's been around forever doing these things and very well known and respected. And Gary joined us at this last one at the Commons out there for the Earth Day event. And it was really great to have his assistance and his passion there. And I also want to call out Arjun, who manned the table And he was right there on the spot when people had questions, and he really handled himself well beyond his years of experience. And it was awesome. And to have such a variety of people from one age range to the other and experiences from one to the other representing the club. I mean, how many places are there that have the quality across the line like our organization does? And everybody's volunteers, and everybody's egos are